have been interested for 2 years today. So, first of all, so my name is Pierre-Brice. I work in Grenoble in France at INRIA. Just one slide. So who am I? So I started working in biped robots quite a long time ago. In '97, I did my master's thesis in biped robots. I did my PhD thesis on biped robots, and now I will tell you about biped robots. You can see a constant there. I was joking when I defended my PhD thesis, saying, well, you know, there's still at least 10 more years to work on that. And now it doesn't make me laugh anymore. And I hope that in 10 years I stop working on biped robots. So during this time, I already have some achievements I'm quite proud of. So what I mean is that, well, you can trust me, at least I hope. My algorithms have implemented the HRP2 robots. So one of the HRP2 robots, I will show you the picture if you don't know it. One of them in Japan uses my algorithm every day. That's the standard algorithm in this robot. And the Now robot, the OmniWalk, the latest algorithm that you have in Now robots, is in fact an implementation of my papers. They didn't ask me for my algorithm. They wanted to recode it their own way, but it's one of my algorithms. So if you're happy with it, you can thank me. If you're not happy, it's there. However, I never participated to any RoboCamp. So what I'm going to tell you is how to make those robots walk. What are the standard algorithms? But of course, if you want to win the RoboCamp, you want to be faster than the standard algorithm, so you want to be better than what I showed you. So I'm not going to show you how to win. I just show you how the standard thing works, so that then you can try to improve it, and then share with us your improvements. So, what I propose to show you today, so first of all, we'll be discussing the dynamics of leg locomotion to show how this impacts the stability and then how you analyze this and how you can propose solutions. Then focus on how you generate dynamic working motions. Then we will focus more precisely on motion and force control. And those three parts are what appears in the lecture notes. So this is a chapter which will be in the Handbook of Robotics next year. So just an extract. And basically doing for those three things, I will follow the flow of the notes, so you can follow and then take notes if you want. You have then more precise references in the paper notes. I skip a lot of things in the notes, so here I just focus on the most important things, but I'm sure you can follow with it. But then I wanted to add also some details about how you do compute those things, which are not in the chat. So I'm going to speak about dynamics and stability. So just to know who knows Lagrangian dynamics. Okay, so some of you who knows Newton and Euler equations. Okay. And who knows Lyapunov? What is a Lyapunov function? Okay. So some of you, so here, this will be the hardest part to follow in the talk, the beginning. So it's good, everybody is well awake. However, if you don't know anything about Lagrangian dynamics and Newton and Euler equations, some of you apparently will have a problem with that. It's not that important. I want to show how you go from the abstract model, complete model of the robot, how then you end up with some simple equations. So when we end this with some simple equations, and then you can follow from here. So don't be afraid by that. So I guess that if you are here, it's maybe because you want to shape the future, you want to work on help improve robots in the future. And I think it's always good to start, if you want to know how to improve in the future, it's good to know where we are, and then it's good to reflect on where we were, what brought us here, and a little bit about the history. So I'm going to show you a few videos so that you see what was the progress 50 years ago, 30 years ago, 15 years ago, and then you can see where we are now with this long-term view. So in the 60s, it was quite impressive. I'll show you the video, work so done in the US by Ralph Mocher. walking truck. And you will see it's a very impressive truck on 4 legs, and it walked already 50 years ago. But there was no computer control at that time. It was man controlled. So there was the man inside the truck and who was controlling all the 4 legs. And of course, it was very tiring. After 50 minutes of concentration, the guy was off, flat battery of the human controller. In the 70s, began the main research on leg robots began in the 70s. Especially you have very famous Waseda University began building humanoid robots at that time. Professor Ichiro Kato there. And that's impressive because 40 years later they are still working on humanoid robots. So during 40 years, during full 4 decades, they are having a driving force in leg robots. But by the end of the 70s, beginning of the 80s, all leg robots were walking with quasi-static motion, so slow motion. However, you have one great achievement in the mid-80s was the adaptive suspension vehicle. So this time it was an hexapod carrying a human driver, but the human driver at that time was only using a joystick. And then you had a fully autonomous motion. I'll show the videos because that's really impressive. To think that, well, 30 years ago, you had already great things happening. But as I told you at that time, quasi-static motion was the rule. And it was about in the beginning of the 80s that in Tokyo University, I don't mention it, but in the written notes, you had the first truly dynamic walking biped robot. So it was 30 years ago. But what's even more impressive was the work done by Mark Raybert in the MIT Leg Lab. Mark Raybert, if you don't know him, when he left the MIT Leg Lab, in mid-90s, he funded Boston Dynamics, which now builds the Big Dog robot and Atlas and Petman for the DARPA challenge. So you see, once again, a huge driving force for leg robots here for 30 years. But the big shock was 50 years ago. Honda revealed their prototype. It was a P2, it was before Asimo. It was such a shock at that time that the video of their human robot was aired on every national TV all around the world. It was really impressive. And you can see, when you see these videos, that, well, in the last 15 years, well, maybe we haven't got much further in some way. So, just spend some time. This is the walking truck. And then so you have the driver, which is here, and you can see that when he lifts the arms and the leg, he controls everything. But I guess it was quite cool to be there, I'm sure. Because you have this big truck, then you have maybe can I go to, no, sorry. Here. Because you can see it move a Jeep there. So you can see so much power in this. So that was kind of ideas they had at that time of what a robot could be helpful for. So just showing, so this is the hexapod built in the mid-80s, so in the US again. And so you can see a great improvement 20 years later. Once again, very impressive. Then you have the dynamic hoppers at MIT Leg Lab. And so it is, so just a personal note, it's by seeing these videos at that time that I decided to work on leg robots. I thought it was really great to try to do the same thing. But then, big shock in 1996, the Honda robot. And just at that time, I was beginning my PhD thesis, and then appeared this robot. And with some of my friends who were just wondering, should we just stop? Problem is solved. Why do a PhD thesis on that? And yeah, 15 years later, you still have students making their PhD thesis on this topic. However, you can see that it was already quite impressive. really impressive. Okay, so I think the question is, how the problem looked solved at that time. What is still not solved yet, and why do we still need to work on this topic? So this is an open question. I won't give you the answer, but just try to think about why we still are still working on that. Okay, so now equations. The dynamics of leg locomotion. Everything starts with how you describe the posture of a robot. And this will impact all the rest of the equations. When you want to describe with the minimum set of coordinates what's the posture of your robot, you need, of course, you're used to using joint positions, which here we call Q hat. And you also need, of course, to describe the position and orientation with the environment. So position and orientation. And here you can see an obvious structure, and this structure reflects in what we call the Lagrangian dynamics. So this is the Lagrangian dynamics. For those who don't know it, that's just a more general way to write the dynamics of a multi-body system like a human robot. And basically it's a generalization of usual things. It's written in a way that you can easily see that here you have the mass, here you have the acceleration, here's the acceleration due to gravity, and then you have forces. You have joint torques, contact forces, and here inertial forces like Coriolis effects and centrifugal effects. So basically what you have is like the Newton equation, you have mass times acceleration equal the sum of forces. Okay? But so here the mass is in fact the mass matrix, which is the size of the number of degrees of freedom of your robot. And the acceleration is, of course, the acceleration of all these degrees of freedom. And then you have this structure appearing again. What you can see is that the joint torques have an effect only at the level of the joint motion. And so if we suppose that we don't have any problem with joint torques, then at least we have some problem, so meaning that you don't have any strong limit on joint torques, then you can always realize whatever joint motion you want. But here you can see that you have some part of the equation of dynamics where the joint torques don't have a direct effect. And what you will need is contact forces. So let's focus on those two parts of the dynamics. In fact, you can show very easily that if you take the lines here, so you use a combination of joint acceleration, position acceleration, and rotation acceleration. But then this combination gives you the mass of the robot times the acceleration of the center of mass. And here what you have is, in the same line here, you have the sum of the forces. So what you have is in fact the Newton equation for the whole of the robot. Mass times acceleration equals sum of the forces. So gravity acceleration and contact forces in this case. The third part here, in the same way, you can show that it's in fact the Euler equation for your whole robot. So then we are going to focus on those two things, because here, those two equations don't depend on joint torques, and you can see that you can then make a motion of the center of mass only by using contact forces. So you depend on contact forces to move. The Euler equation, I write it that way. So here you have the derivative of the angular momentum. The angular momentum, you have this nasty equation, but that we don't care about. So you have the derivative of the angular momentum, which is equal to the sum of torques. So what happens if you have no external force, no contact force, zero gravity, and zero heat? So obviously you have the acceleration of the center of mass, which is zero. So if you start with zero velocity, you don't move, you can't move. And here you have conservation of the angular momentum. Let's look at a simulation. Here you are in space. It's a simulation in space. You have this humanoid model which is walking in space, no external force. So conservation of momentum. And it was zero in the beginning, it is zero in the end, but it has turned. And when I ask my master students, so where is the mistake? Have I made a mistake in my simulation? And unfortunately, at least half of them believe that I made a mistake in my simulation. So I didn't, and this is a real dynamical effect. You have conservation of momentum, which is always equal to zero, the angular momentum, and yet it moves. Who knows why? So that's an important thing to realize, in fact, here. That, so if you, there's a mathematical word for this angular momentum, it's called non-holonomic, which means that even though you keep this value constant, you don't have any constant in x. So you don't have any constant in theta, x, and q. So what that means, more practically speaking, is that here, even though, so I can show you maybe myself, even though I would have no contact force, if I move my hand like that, okay, I will of course move my body in this direction a little bit. Now if I move my hand here, I don't create any rotation. And if I move it like that, I will create a rotation the other way, but slightly less, because I have less inertia in my hand. And then I can, so if I do it like that, I can rotate. This is exactly how cats fall back on their feet. They can't push on anything. They can't push on the air, it's too thin. And yet they can move around. What they do is that they modify, they do exactly this motion with legs. Okay, so when they modify, and it appears to be exactly the same motion that you do when you walk. So when you walk, by doing that, okay, you change the inertia of your legs while moving forward and backward. So you create some rotation. So here you create some rotation even though you have zero angular momentum. So now the question is, of course, when we walk, we don't rotate. Even though we have this effect. Here it was a no-cap motion. It was recorded on the humanoid replay. So that's a true walking motion. And if you do it with zero angular momentum, you turn. And when you do it now on the ground, you don't turn. Of course, that means that you have a non-zero angular momentum when you walk. So you have this very strange thing to grasp, that if you impose a zero angular momentum to the robot, it's going to fall. It's going to turn exactly that way. Because when you walk, well, you have a non-zero angular momentum. I'm not going to spend too much time to discuss this, but just saying that this is a very complex issue, the problem of angular momentum. And that's maybe because it's tricky, and that I guess is the main reason why a lot of people just avoid it. They say, oh, well, we don't care about angular momentum. No. Consider that then it would be a perturbation. Because it's a very tough problem to deal with. Okay, so we have these equations of motion. Now what happens when you walk on a flat ground? Okay, let's suppose we walk on a flat ground. So what we are going to do is sum those two equations. But first I multiply this one by C cross product. So I take the cross product with the position of the center of mass. Okay. So C is the position of the center of mass. So I take C cross times this and C cross times this, and I add. So by adding, I will remove this term here. This is what happens on the next slide. So I have C times the left part of the Newton equation plus the left part of the other equation, and then I have this result here. And then I divide this by the z coordinate of the Newton equation. So here I take the z coordinate, z coordinate, z coordinate, and I divide term by term.
Excuse me?
Yes?
What is pi?
Oh yes, sorry, it's the position of the contact points. So yeah, so here you have the position of the contact point with respect to the center of mass. So then that gives you the torque generated by the contact force. Okay, so we do this transformation here, and then we focus on the x and y coordinates here. So we So here what we have is that we have first the x and y coordinates of c times the z coordinates of here, and then you divide by this, and so you just end up having the x and y coordinates of the center of mass. Then here, what you have is the z coordinate here times the x and y coordinates here. So you have this equation here, and you have the mass which is given. Okay. Then here you have this term here, and you have a sign matrix here because I changed signs surreptitiously in the equation, but that's a detail. And here the important thing is that if I work on a flat ground, let me consider that the z coordinates of all the contact points is equal to 0. So the pi z is equal to 0. So here we'll have the z coordinates times the x and y coordinates, but that's 0. And then I have the z coordinates times the x and y coordinates here. So that's what I have here. The z coordinates of the force times the x and y coordinates of the contact points. So that was quite boring, but the end point is interesting. What appears here, you have a sum of the position of the contact points, but this sum is weighted by the normal force. What this is, you have the contact points, you have the vertical force, normal force, and then you have this point, which I will call Z, which is the weighted sum. This point is the center of pressure. And an important thing is that if those forces are only positive, and they can only be positive if you can only push on the ground. So if you're not sticking to the ground, they must be positive. And if you are not sticking to the ground, then this center of pressure must be inside the convex hull of the contact point. So inside the support polygon. That will be an important rule. Okay, so we have this equation here, and here I just rewrote it so just redispatch the terms. So I call this Z now, Z, X, and Y. So I consider C minus Z plus this angle here, and then here I have the acceleration along X and Y of the center of mass. So here you can see that I consider the X and Y coordinates of gravity. Why am I doing this? Well, because here I consider a flat ground, but it can be flat but not horizontal. So here what I took is the Z coordinate, which is orthogonal to the ground, but I wrote a completely general equation, even for walking on a slope. So this is correct, whatever the flat ground you are walking on. So you have some gravity along X and Y if you aren't in the tilted ground. So here you can see three terms. One is acceleration. You have, and this acceleration of the center of mass parallel to the ground is related to gravity, to this vector between the position of the center of mass and the position of the center of pressure, and then the angular momentum. So you can visualize this here. If you have the center of mass here, and the center of pressure there, and the center of pressure must stay in the support polygon. So you have a vector which goes from Z to the center of pressure. To this vector you add the effect of gravity, if you have some gravity along your plane, and then the angular momentum. And this gives you the acceleration. So in case you are walking on a horizontal ground, you don't have this vector. In case you want to avoid dealing with the angular momentum, then this vector is directly this. And you can see then what you can also feel, that when the center of mass is here and when the center of pressure is there, then obviously the center of mass is going to accelerate in this direction. Okay?
There's no need to take shear stress into account.
So first of all, here I'm dealing with supposedly rigid bodies. Okay, so what I understand as shear stress here would be maybe the rotation of
shear stress of
okay, so
the touching points.
okay, so which would be related to the friction coefficient. So it can be a constraint. Here I haven't spoken about the constraints on the contact force. Okay. I just focused so far on the fact that it can be only directed upwards. So in the paper I discussed a little bit about friction. It happens that it's not such a problem usually for walking. Okay. So it hasn't been the main focus. So you can have some problem with friction when you have both feet on the ground, because then if you don't synchronize the two motion, then obviously you have some slipping motion. It can be a problem if you want to accelerate very fast, because of course the acceleration of the center of mass is related to the force. But it happens that normally robots don't accelerate that much, and it's not such a problem. I have colleagues in Japan, I remember, they made a paper on how to deal with these friction constraints, and they had to work hard to find the surface where it would be a problem. So they really had to use a wet metal surface so that a robot would slip on it. So most situations is considered to be non-problem. Now, if you want to introduce it, you can. I'm not going to discuss this because it's not the main problem. But of course, it's possible to deal with it.
With our skating robot, that turned into quite a challenge then, because skates are interesting in that respect because the ground reaction force is very strong sideways and basically zero.
Yes, but usually in this case you consider the limit, which is you consider to have absolute friction in one direction and absolutely no friction in one direction. So once again you just get rid of this friction coefficient by considering that you have a non-running constraint, that you can go freely in one direction and absolutely not in the other direction. So that's usually what's done. Okay, so we have this equation here. So what happens now if you walk on a horizontal ground? Then you get rid of this. What happens if you consider that you walk more or less horizontally, so that you have very small vertical acceleration? So you can forget about this term. And what if you just consider that, well, let's forget about this term, because it's really a problem. So you end up having this model here. So this is where I will stop speaking about mechanics. So now you just have to focus on this equation. And in this equation, you still have the main component, which is the acceleration of the center of mass is related to the position, the relative position of the center of mass and the center of pressure. So it happens that this equation, so it's linear, obviously. It's linear because if you consider that you don't have much vertical motion of the center of mass, this is a constant and this is a constant. So it's a linear equation. It happens to be equivalent to the equation of an inverted pendulum when you linearize it. So it is often called the linear inverted pendulum model, which is how it was called by yesterday. So, but you can see that it's not just a linearized equation of an inverted pendulum. How we derived it so far, this equation is absolutely correct in all cases. There was no approximation here. The only thing that we did at that time was consider that we walk on a flat ground, because that's the only way to introduce the center of pressure. If you don't walk on a flat ground, there's no definition, no good definition of the center of pressure. So here we just walk on a flat ground, and from here to here, we just consider that we work on a horizontal ground, and we walk without much horizontal motion, vertical motion, so only horizontal motion. And the only approximation that we made was not considering this. So it's not just an approximate model. I want to insist on this. So Now we focus on this equation. So what if you happen to make your steps here, and for some reason you cannot make steps beyond this red line? It's a gap. You can't walk there. And what happens if your center of mass is just going outwards here? So as we saw in the previous drawing, since your center of pressure must be somewhere here, and your center of mass is suddenly going there, it's going to accelerate in this direction endlessly. You cannot do anything else but accelerate in this direction. So have a divergence. You can solve this equation, of course. It's a linear equation. So it's a linear equation, but in this equation here, z was not chosen. It's a free variable, and it can be freely chosen in this set. So maybe we solve it with an inequality. We just said that z is on this side. So then we have the acceleration which is going in this direction. So you solve it, and you have exponentials appearing. Of course, it's a linear, second-order linear dynamics. So what you can see is that if you solve this equation, that you diverge, and you diverge exponentially. And that will be an important thing to use later. So obviously you are going to fall. That's what it means. So what you can see is that you can be in situations where you haven't fallen yet, but you are bound to fall. You are going to fall whatever you do. If you can't here make the proper step, you are going to fall. And there's a mathematical theory behind it. It's called viability theory. You have in such situations where you have states where whatever you do, you are going to fall. And this then will be called a non-viable state. And you have situations where if you do the right thing, you can avoid to fall. Of course, if you do the wrong thing, you can always fall. Okay? So it's just an option between if you do the right thing, you can avoid to fall, or whatever you do, you're going to fall. And of course, we want to be in a state where we have an option to avoid to fall. So our goal is to always keep our state viable. So the problem is, how can you know if you are viable or not? How can you know that it's too late? Whatever you're going to do, you're going to fall, so you should avoid the state. How can you know? Of course, you can know some special cases. So like fixed points. If you are standing like that, you know it's a viable motion. If you have a motion which leads you to a fixed point. Okay? Or if you have a cycle, like if you are walking, if you cycle, or any motion which leads you to the cycle. So you can know some special cases. But generally speaking, give me the state of the robot and tell me if it's viable or not, then you have to test all the options, all the possible motions, in order to decide if you find one which allows you to move. So in the general case, deciding whether a state is viable or not cannot be answered. So it's a very interesting mathematical theory, but with no use to engineers. However, in our case, remember that for this simple dynamics, if you diverge exponentially. So you know that if you focus on the integral of the norm of any derivative of the center of mass, see, because if you diverge exponentially, then it means that the speed diverges exponentially, the acceleration rate diverges exponentially, any derivative diverges exponentially. So if you focus on such an integral, if a motion falls and this integral is infinite, and if it's finite, it means that you have a motion which avoids to fall. So maybe if you try to minimize this integral, okay, if you try to do some optimal control out of it, and trying to keep it as low as possible, and hopefully finite, then you will choose a motion which avoids to fall. This way. Okay? But unfortunately, here you have an integral till infinity. You have, because you're never sure if you haven't reached infinity. And of course, you can compute on an infinite time. And also add some order, it wouldn't be interesting anyway to have an infinite plan. You're not interested in that because the situation might change. So, another term which was introduced by Pierre-Brice 7 years ago was the idea of capturability. So instead of trying to know if you can avoid to fall in the end, maybe in a century, well, let's focus on if you can avoid to fall in 1 step, or 2 steps, or 3 steps. So you just decide a finite amount of steps, so then you have a finite time problem to decide if you can avoid to fall or not. So that's the idea of capturability. Impose that you can stop in 1 step or 2 steps. And his claim, which is, I think, quite convincing, is that that's all you need. And usually when you are a human, either you can stop in 2 or 3 steps, or you're going to fall anyway. So the difference between being able to stop in 2 or 3 steps and then the more general approach, the difference is very thin. So that's just enough to consider that you can always stop in 1, 2, 3 steps. Now, how can you decide if your state is capturable or not? Hopefully, Pierre-Brice continued his analysis of the situation and introduced what he called the capture point. And that was perhaps the most important result in the last decade, realizing the importance of this capture point. In fact, so the capture point is just T here. So you just take the position of the center of mass, and you add to it its speed, weighted by the omega, which is the time constant of your dynamics. Okay, you just consider this value here. In fact, this value has been introduced in many different ways around the same time. So Jerry Pratt called it the capture point. I don't remember the name. So in biomechanics, it was called the extrapolated center of mass. And then engineers in Honda, working on Asimov, also introduced the same idea. They called it the divergent part of the dynamics. And those 3 terms correspond to 3 different properties of this value C that we're going to see in this slide. So if you just reorder this equation, and that's what we do here. You have then the speed of the center of mass is proportional to the difference between C, the position of the capture point, and the position of the center of mass. Here you have a first order linear dynamics, but it's converging. You see that since omega is positive, C is converging to Xi. So Xi is the point where the center of mass is going, which is obvious if you consider this definition. Okay, so that's why it was called the extrapolated center of mass. That's really where your center of mass is going. And then if you introduce this change of variable in the linear dynamics that we have here, just rewrite things very, very simply in a few minutes, and you end up with this dynamics of the capture point. So the speed of the capture point is proportional to the position of the capture point with respect to the center of pressure. Okay? But here it's a diverging speed. So here, C is moving away from Z. The capture point is moving away from the center of pressure. So the center of mass is moving towards the capture point, but the capture point is moving away from the center of pressure. So you can have this in this plot here. So if you have the center of mass here, the center of pressure here, you have the speed of the center of mass, and then you have the capture point, which is here. So what happens is that the capture point will go away, so the speed will be in this direction with respect to the center of pressure. So the capture point is going in this direction. But the center of mass is going towards the capture point. And the combination of those two first order dynamics gives you an acceleration of the center of mass which goes in this direction. So it goes with this speed, but with this acceleration. So it will go like that. Is it clear? So, what happens is that here we have the two, so the second order linear dynamics that we have here is in fact has been rewritten here as two first order dynamics, one being converging and the other being diverging. So now you know why the engineers in Honda called it the divergent part of the dynamics. They said, what we should do is focus on this value xi and control it, because that's the unstable part of the dynamics. The motion center of mass, no problem. It's going to follow xi. So what you just need to control is this value. And then it's called the capture point. And why? Because if you see the on the plot here, if xi is here, then you can decide to put your foot here. And if you decide to put your foot here, then you can decide to put z exactly above xi, below xi. So in that case, z and xi are in the same position, horizontal. So xi doesn't move, and xi doesn't move, and the center of mass converges to it, and then you start. So you can see it in the equation here. Here you have 0, so here you have 0 speed, and then you have c dot, which is converging to 0. So the capture point can be used to tell you that if you put your step there here, you're going to stop. So that was quite a new. You see very simple equations, but a major observation in understanding the importance of this. So how are we going to use all this to generate dynamic walking motion? Now I'm going to have a big chunk that I think it would be interesting to maybe not interrupt. So I'm not sure if it's time to have a pause now, or we have been through already 40 minutes talk, and then we would go for another 20 or 30 minutes now. So either you want your break now, because we went through the hardest part of the talk. This was the hardest part. A lot of equations, I'm sorry about that, but I hope that it can give you the connection between the whole body model and what we do to generate working. So, I leave it to Sam to decide.
Yeah, actually the break is scheduled in about 37 minutes.
Okay.
So we have time.
So we have time. So, how to use this? Early schemes in the 80s and 90s were the following two ideas. First idea was, well, we have this wonderful numerical tool that people in numerical optimization work on. You can solve trajectories for rockets to send rockets to Jupiter. So why not make a robot walk? So just write down the equations, as we did, the whole equations, and just ask your numerical optimizer to find you a good trajectory. To say that you want to minimize the energy, for example, and that's it. Problem is, it doesn't work. Numerical methods are not that clever. So it's only 10 years ago that it began to work, and only in simple cases, and it takes a lot of time. And so one of the best results in this field, I think, is obtained by Katja in Heidelberg. But apart from her, very few people managed to just say, this is the whole dynamics of my robot, just give me a walking motion. That doesn't work. Then you have a very interesting idea. It was the most successful idea, which was proposed by first by Professor Quadratic in the end of the 70s, and which he called the artificial synergy synthesis. The idea is that, so we have this equation here, and the observation that this equation is only in 2 dimensions. So here you have the connection between the motional system of mass, the positional system of pressure, and the environment. But so because the position of the center of mass is constrained, you have these 2 equations that give you 2 constraints of the motion, but only 2 constraints. What about the rest of the motion? I haven't spoken about joint motion. After the first few slides, I spoke about it. So his idea here was to say, well, you can choose any joint motion that you want, at least not a too crazy one, and then just assign a few degrees of freedom of your system to satisfy this constraint. So his original idea in the 70s was to say, well, let's use pre-recorded walking motions. Okay. And then you just use the arms to keep your equilibrium. Okay? So what he was using is in fact so predefining the whole motion, joint motion of the system, except for 2 degrees of freedom, which would modify here the angular momentum of your system. So it was a purely theoretical idea in the 70s, but it was realized in the end of the 80s in the Waseda University that I mentioned. So they had this robot which was playing a predefined motion, and you had inertia wheels there turning around, and it was, so they were turning a lot in order to compensate for all the dynamical effects which were because of the pre-recorded motion. So it turns out that this idea has been followed too closely by people later. They said, oh, maybe we should do that. So what we should do is pre-record a motion and then use a few degrees of freedom to control. And that gave rise to what's called the ZMP approach. Because here, of course, since you predefine the position of the steps, you can predefine the position of the center of pressure. Okay? So then it's just a matter of then solving this equation to find how to equilibrate your motion. So here what you would have is that you predefine most of your motion. So of course that limits your reactivity. Here, you see this idea was used to track a single motion, but what if it cannot be tracked? Then you just you have no other option. So this robot in Waseda University was walking with his arms turning around just to equilibrate, but you shouldn't push it. Because then the arm is going to try to equilibrate more, but if they can't because you have joint limits, well, it's going to fall. But you can see that it's a limit that is not imposed to you. You are free to decide. You can still use this artificial synthesis and still use it with free step motion. And that's something that we're going to discuss. But just mentioning that this general idea of saying, well, most of the motion is not relevant, and only a few degrees of freedom are important, and especially the motion of the center of mass and the angular momentum, gave rise to a very interesting domain of research, which is called templates and anchors. And I believe maybe Moritz Mars, because he mentioned it in his lecture presentation, so I don't know if he talked about that, templates and anchors. But usually that's the kind of thing that people in biomechanics use. And basically, that means, well, focus on a few degrees of freedom and forget about the rest. And that's exactly the same idea. So how can we use this, but without the rigidity of having offline generating motion? So what would be interesting in online motion generation, because then, of course, that will help you have better reactivity. If you have perturbations, or if you want to change your goal, because the ball you want to go there, but then the ball is there. So you need online motion generation for it. The problem is, if you keep regenerating your motion, so you keep recomputing your motion every millisecond, for example, how can you make sure that you don't change your mind every time, and in the end you end up being unstable? If you say left, right, maybe you're just going to fall in the end. So how can you make sure that in the long term, changing your mind doesn't destabilize you? So here we are going to build on this observation that we made, that maybe this integral of the norm of any derivative of the motion, especially issue of the motion of center of mass. Because maybe we know that if we want to keep this small, then we stay stable, we stay viable, then stable. So let's do, I propose to have just 4 slides on optimal and model predictive control. Because we will see that that's what is used in every robot, walking robot in the world, or nearly every robot. We are going to see in a few slides, but let me tease you with that, how the Asimo robot works, how the Toyota robot works, how the Sony Curio used to work, and how the HRP2 works, and how the Nao works. So all those robots, they all work the same set of ideas. Or at least you can see that they share a lot of similar designs. So, speaking about first optimal control. So here I switch to some discrete time dynamics. So you have the current state of your system, and then you decide for a certain control that gives you the next state. Okay, so you have this discrete time dynamics. And then what you want to do is minimize an infinite sum, which is a discretized version of our infinite integral. So you have a result in optimal control that under some technical conditions, which are satisfied here, but you should always read the fine prints when you sign the contract, so you should always take care about those technical assumptions. Then this function that you want to minimize can be used as a Lyapunov function. So I'm not going to speak more about Lyapunov functions, but basically what that means is that this integral is going to decrease with time, which can look a bit obvious. That, sorry, if you have this integral starting at the time t0 and then starting at the next time, of course, the amount of time for the integral is going to reduce, so this integral is going to decrease. And since it decreases, if it was finite, it will stay finite. So if you manage to have a controller which continuously minimizes this and keeps it decreasing, you will stay stable. You are going to avoid to fall. So optimal control will be an option. Now the problem, of course, is that we still have this infinite sum. And that's where model predictive control comes. In model predictive control, you have this milestone paper. What they propose to do is, well, use a finite sum. But then after these n steps of control that you want to anticipate, just impose that you have reached your goal. Okay? And in this case, you can show that this function is still decreasing, so that this truncated integral is decreasing. It's truncated, but you have imposed that you have reached your goal in the end. And here you can see the connection between viability and capturability. In viability, we're considering the infinite integral. But with capturability, it was proposed that maybe you consider a finite motion, but you impose that you stop after those 2 or 3 steps. So in fact, this switch between optimal control and model predictive control corresponds to the switch between potentially infinite viable motions and capturable motions. So this is the general theory about MPCs, but in fact, you have many variants where you can modify how you deal with this constraint, modify how you deal with this minimization, and you have 2 extremes. And we're going to see those 2 extremes because it's interesting to observe that for walking robots, only those 2 extremes have been used. The first extreme is, well, forget about this minimization. You just find a motion, so a control law, which leads you to stopping after n steps. Just find it. And then play it. And then, if you have a perturbation, then recompute. But of course, it doesn't work like that. It's not because you will have the same problem that if you keep recomputing, then you might end up falling. So here I have a pretty complex way of deciding when you should recompute and how you should recompute in order to be sure that you are stable. So stability can be kept only if you recompute in a proper way, which is quite complex to code. Or you have the other extreme, which is just forget about the constraint, just consider a truncated sum, and if your n is big enough, if your horizon with which you anticipate is long enough, then you can show that it's stable also. So, from the original MPC scheme, in one case you just follow the constraint and take n big enough. And for walking motion, n big enough is one step. One step is big enough. But of course, the longer your horizon, the more better your choice. You anticipate more, so you can make better choices. And usually people just anticipate for 2 steps. Okay? So they optimize it for 2 steps. Some people try 3 steps, but usually it doesn't improve anything. So 2 steps is fine. So either you just truncate for 2 steps, or you don't want to minimize anything, and you just impose that you stop after 2 steps. Okay, so that goes to these 2 extremes. Now we can see we're ready to just browse through all the methods which are used on the robots that we know, and just see how they fit with this general theory. So first of all, because that's historically the first approach, as I mentioned, predefined footsteps. Okay, so far, people suppose that the footsteps are given and are fixed. And then first, methods which consider the capturability constraint and no optimization of the derivative of the center of mass. Then you have, so historically, it was at a university. What they use is, in fact, a multiple mass model. They consider multiple mass, but here you have the same equation for multiple mass. You have the position of the center of mass, the acceleration, and multiplied by the vertical acceleration, vertical position. So this, then you have an iterative process to solve, to make this value converge to a predefined center of pressure. Okay, so you have a trajectory for a center of pressure, and then you solve this equation to find motion, which will satisfy the dynamics. And they use a quite complex iterative process based on fast Fourier transform. It's really very complex. And they impose in some way, but it's not very clear in the papers, that they must always be able to stop within 2 steps. So what they do is just compute a motion, which is feasible with respect to the dynamics here, and which is able to stop 2 steps, then in 2 steps. It should always be able to stop in 2 steps, but it doesn't stop every 2 steps, of course. It's just, when you make 1 step, you just impose that you should be able to stop 2 steps later when you make 1 step. So it's always a security. And as we saw, it's this with the MPC theory, by imposing this constraint is always satisfied. If you don't have any perturbations, and then you don't have to follow this rule to decide when to recompute, well, it's going to be stable. And just to show you, because I haven't shown in the historical milestone, this is the typical motion that you obtain. So here they were doing some emotional motion, so what happens if you want to dance or things like that. But basically here you see the use of the scheme. See, they always impose that in the future 2 steps the robot is able to stop, and that's enough to obtain a stable motion. Then what was done, for example, in the Technical University in Munich, they built 2 quite impressive robots, Johnny and Lola. Well, they decided to use 3 mass model. So the same kind of model before, but with only 3 mass. Okay, 3 mass means 1 for the upper body and 1 for each leg. So that's an approximate model. Okay, and then they say, well, we fix the footsteps, we fix the motion of the center of pressure, but we leave 1 or 2, we have 2 degrees of freedom free in this motion. So this motion is predefined except for 1 or 2 degrees of freedom. And these 1 or 2 degrees of freedom are used so as to impose this constraint. So as to impose that in the end of the motion, 2 steps later, the center of mass is there. So, here it looks like a capturability constraint. You just impose that the center of mass is fixed there. But you see that there's no constraint on the CO speed. So in fact, capturability is not really constrained.
So, das Polizei.
Polizei?
Ja.
Das ist wahrscheinlich nur eine Polizeiübung.
Ja.
Die sind hier öfter. Aber vielleicht müssen wir die Fenster schließen.
Okay. So here they impose the position of the center of mass for some time and not speed. So capturability is not constrained. So in some way, there's a failure here in applying proper theory. Hopefully, systems are robust to design errors, so it works. But regarding the theory, there's a failure here. Maybe we can show you a video of just what happens to show you that just following these simple rules, I'm learning how this works in motion. Professor Louis and Thomas Bushman. So Thomas Bushman was doing his PhD thesis on the control of Johnny and Lola, and he was the one who proposed this scheme, I showed. What about the Asimov robot? Interestingly, the people in Asimov made the same choice as Thomas Bushman in Johnny, or maybe the opposite. In fact, he got inspired by their papers. So people in Honda, they use a 3-mass model. They use a predefined motion, predefined footsteps, predefined trajectory for the center of pressure, except for 1 or 2 degrees of freedom, which are used to satisfy this constraint, which is that the capture point, and this time they use the proper capture point constraint. The capture point, after a certain time, so here 2 steps later, should be here in the control position. Okay? And that's how they generate walking motions online for the Asimov robot. Now you can try to do better. Just following other options, there was a long history of great robots at Tokyo University, Todai. And so Dr. Nishiwaki, it was 10 years ago, more than 10 years ago, on the H7, they had huge robots, H1, H2, H3, until H7. And then they moved to HRP2. So proposed this scheme. And in fact, it's the same scheme which has been used later by Toyota for their human robots. The scheme is the following. You can recognize the cool dynamics. And in fact, in this cool dynamics, the angular momentum is supposed to be fixed. And what's going to be adapted is the exact motion of the center of mass. And it's going to be adapted by an iterative process so that the center of pressure, because here we have the equation for the center of pressure, converges to the center of the footsteps. So the footsteps are predefined, as before, and then you try to find a motion for which you put the center of pressure in the middle of the footsteps while imposing these constraints. And here we move back to this approximate capturability constraint. You only impose the position of the center of mass, but it works. The last one for this series with predefined footsteps, what was used on the Sony Curio robot, which was a very intensive robot. Unfortunately, it was terrible news when they stopped working on the Curio robot. So what they did was using this single mass model that we've been working with, and instead of imposing that it follows a predefined motion and just leave 1 or 2 degrees of freedom free, they say, well, let's try to minimize this squared sum of, so we try to follow this as much as possible while imposing this constraint. So here constraint on both position and speed, so that imposes capturability. But maybe that imposes not only capturability but also stopping there. Okay? So you can see always the same if you go inside the equations, below the equations, because everybody will write his own ideas and systems in different forms. But you can see, in fact, if you take everything in the same form, they all follow the same idea. So another group of propositions were still with predefined footsteps, but without capturability constraint. Because for all these schemes here that we saw, since they don't minimize anything except for this one, but this one doesn't minimize, so it minimizes, in fact, it tries to follow the dynamics here. So it doesn't minimize in some way, in a proper way, an integral of the acceleration or jerk or derivative of the center of mass. So all of them, the stability rests on this capturability constraint. So it means that if you have to adapt to a perturbation, to recompute, you need, as I mentioned, this complex decision as to when to recompute, and how to recompute. So in fact, in all these schemes, there was no possibility to recompute, because they didn't go through all this complex process. So in all these schemes, the walking is pre-computed and then replayed. So that means no reactivity at all. So that's where comes solutions without capturability constraint, but focusing on minimizing integrals. And here you have one of the most influential papers. It was proposed by Kajita in 2003, 10 years ago. And so it was called preview control of the ZNPs and NP preview control. And what he says is that, well, let's minimize this integral for two steps. Okay, so we have this finite horizon and we want to minimize this integral. So here what we have is that it has a predefined angular momentum. Okay, and then he wants to compute the motion of the center of mass such that here the center of pressure is as close as possible to the center of the feet, but at the same time, with some weight, minimizing the third derivative of the center of mass. And that's the key, as we can observe when I was proposing a viability analysis, that if you manage to keep this small, you know that you are going to avoid to fall. So by minimizing the combination of those two things, you know that you have a stable motion which satisfies the equation of the dynamics, the constraint of the center of pressure. That was great.
Why is the jerk of the center of mass a measure?
I mean, what I showed, maybe very quickly, but what I showed here is that if you keep any derivative of the motion of the center of mass finite, then you are stable. Because if you are going to fall, everything diverges exponentially. So you can choose any derivative of the motion of the center of mass. Kajita happens to have chosen the third derivative. That's no. So maybe one option is that one reason. So there are some more intricate reasons, but an easy explanation is that he doesn't want to interfere with the acceleration. He doesn't want to interfere with the speed and position, because he uses already position and acceleration for the dynamics, satisfying the dynamics of the motion. So he wanted just a higher derivative, and that's it. Moreover, of course, you can see that from your knowledge of linear dynamics, that the higher derivative will diverge more quickly. So the higher derivative you consider, the faster you can react to instabilities. Now, of course, the higher derivative means the more noisy your system is. So, well, he chose the first derivative. That's it. And you can choose something else. I will show you that I choose something else in the end. A variant, I call it a Korean variant because it was proposed by some Korean guys, but not from a famous university, so I can never remember. You have the reference in the video. Just know the same thing, but let's consider that the angular momentum is not fixed. Let's consider it's a variable. And then, so if you consider it as a variable, then you want to minimize it in some way. And you can do that. Just mentioning that you can use the whole exact model and still compute walking motions. And of course, they claim in their paper that have better results. Then you have my first proposition. Well, what is my first successful? Much later than my PhD thesis. So because I visited the lab where Kajita is working, Kajita, and so I observed this scheme. And I said, well, you know, maybe, so the problem with this scheme here is that you can recompute every millisecond your control law. It's good, it's very good. And if you push the robot, you can have some reactivity to your system. So here, let me remind you that we are still with predefined footstep for these schemes. But still, predefined footstep, that you can have some adaptation of the motion of the center of mass. But here, by minimizing those two things, you are not sure that your center of pressure, here you want your center of pressure to be as close as possible to the center of the foot. But if you have a strong perturbation, maybe it will go outside your support polygon. So maybe your robot is going to fall. So I was proposing, well, let's impose that the center of pressure here, with this model, is inside the support polygon, is inside the convex load. So we'll use a constrained control load. And then we just need to minimize this derivative. So far, I just wanted to be conservative. And it worked, so let's modify as few as possible. So I said, let's keep the first derivative. That's it. And it works. And this is the paper that Aldebaran decided to implement. So in the current method, that's what they use. And so that time the reaction from colleagues was, well, but you saw the constraint problem, and that's much more costly to solve. That takes much more time. You need a QP solver, you need iterative processes. So I believe this was an error from their side. And that's why I'm going to show you a little bit about numerical implementations and why it can be just as fast to consider strict constraints. But before going to walking without fixing footsteps, I just want to just present one idea, which I think is striking, is to me. It was not in robotics, but it was proposed by Michael van de Van in Euro graphics. So it was never used for robots, but it's very striking. What he does, what he says that, well, let's minimize this integral for 1 or 2 steps, okay? And then just recompute it. So that's the same MPC scheme or similar MPC scheme, and he used it to generate such walking motions. The striking thing here is that what he imposes here is that the center of pressure is close to the center of the feet. Okay, fair enough. But here he doesn't minimize the derivative of the motion of the center of mass. What he does here is in fact keep the leg length, the distance between the center of mass and the center of the foot, well, rather constant, because he was generating 3D motion. So here there was nothing related to the stability analysis that I proposed. And yet, it worked. You can see here, the plan is always changing, but in the end it works. Here, the only thing that he does is he poses that he has 2 more steps which are feasible. And that's all. So, I have no theory to explain why it works. It's a very bold idea, and it works. So there is maybe room for thought here, and try to understand, maybe simplify our schemes. Now, what about adaptive steps? Because of course, we had in those schemes some bit of adaptation, but we know that the most efficient way to walk is to be able to adapt your footsteps to what's happening. So here is a paper which now they are in the process of integrating in the future now walking algorithms. In fact, it's obvious. It's obvious. Just take the same dynamic equation that we have, but just don't impose this. That's it. Why impose the footsteps? Just don't impose them. So you have these constraints. So the variables now are the motion of the center of mass and the position of the footsteps. And you have this constraint. Okay? And how do you make sure that your motion is stable, just minimize the integral of the norm of any derivative of the motion in the center of mass. And let's take, for example, the speed, and not the jerk. First derivative, it's fine enough. And let's say, for example, that I want the speed to follow a given reference speed. It looks so obvious. Just write the equation of the dynamics and say, go in this direction. And it works. So I proposed this with one of my PhD students 3-4 years ago. And so you can see that it took me 13 years of research on biological robots to end up with this obvious way of making robots. The most obvious things are not always the simplest thing to discover. Yet, so it works. And here you can see an experiment. So first experiments were done on the HRP2 robot in Japan. I had my PhD student hidden there. And what he was doing, so here it's completely online. And he was saying go forward, go left, go right, etc. Without even informing the guy here, he's nervous. He doesn't know in which direction the robot is going to walk. Because it changes on the fly. And my PhD student was nasty enough not to tell him in advance. So you have this slow but dynamic motion happening, and you can see that even sometimes in mid-air, you know, he was beginning a step and then suddenly walk backwards. So you have this reactivity. See, and you can change the motion online. And what you just say is go in this direction, go in that direction. And then you can plug in vision feedback. So here it was just saying I want to see those. So this is the view from the HRP2 robot. It's accelerating twice. So we'll always go slow in lab experiments. Maybe something that you don't want to walk up, to go fast. But saying, well, I want to see. Let's say that this is the goal, and you want to face the goal, or you want to see the situation from different angles. And I think that kind of thing that we do. Another option, which is, has been proposed recently in Tokyo University, Todai. I mean, can you be more simple than this? This is how they generate motion. So what they say is that, well, let's just impose the terminal constraint. Okay, terminal constraint, which is the capture point, should be controlled to some desired value. After n steps. But then those n steps are free. Just do whatever you want. Put your steps wherever you want, and just impose that after n steps you stop. And that's all you need to have a line decision of replacement. And you will see. And what they did is just free footstep, just impose capturability after n steps. And try to find n as low as you can. Now, of course, if you remember, what I told you is that if you work on the terminal constraint and not with a cost function that I was proposing, then you cannot, it's hard to decide when to adapt to perturbations. It's hard to find when you recompute or not, because changing your mind in the wrong way can lead you to fail. And you can see here that in this case, it was a very special case. They know when and they know how to change, because they know that they are doing nothing, and as soon as something happens, you react. Whereas then it was later used for walking, and you can see that when it's walking, well, they do much more slower perturbations. Because then they have, it's harder to use, to decide when to change. So it works, but maybe not as impressive as the one when it was standing, when you could see this huge push.
But is there a major concern with any kind of motion that we may want to generate on our kind of robot? The fact that we're severely limited in the torque that we can generate in the joints. Like this particular robot can only do that because they use the capacitors to get extra power to the joints. So they can, and that's similarly to the big dog in the Boston Dynamics system and Atlas. they have these hydraulic generators, so
Yes.
they can actually generate motions, whereas for us, most of those would be just impossible because of the constraints on the torque.
Yes. So, I speak a little bit in the paper about some very important result obtained recently. So, deciding what's the best option to react to a perturbation. So, first idea you can use angular momentum, and then it was shown that it doesn't help that much. What's more effective is doing footsteps, adaptive footsteps. But then you have two potential variables. One is the length, and one is the speed. And it was shown that the most important thing is to have fast steps. Because, of course, the more you wait before making your step, and wait means also the time you need to realize your step, then of course, the more destabilized you are in the meantime. So, speed of reaction and speed of execution are, of course, key to robustness. And there you have, of course, the limits of your motors. Yes, definitely. And that's one reason why I was just about to show through some videos of Boston Dynamics robots. And when you see those results, we have similar ones. For example, so this PhD student of mine who did that, that experiment, then he went in postdoc in DLR with Chris and Ott, and they do similar experiments. Just last week, they did similar experiments to this one, pushing the robot where it walks, and it makes a step on the side. But for the same, but it's not more impressive than this. It's just as this. You give it small nudges, and so it's far less impressive than Big Dog or even Atlas. That's mostly because we use actuators with very fast and very powerful, and with dumping properties also. That's the choice. So that's one of the many choices that Mark Rebert made in 30 years ago. In the beginning of the 80s, he just said we have to use hydraulic systems, and he kept using hydraulic systems since then. And you can see the result, which are impressive. Then, of course, the problem is that you need a compressor, it makes noise, and so if you want robots in everyday life, so far the hydraulic system are not ready for. So, what are the key ingredients here? Just to wrap up. So you have the observation that what we want is viability or capturability. You have those two things. And the key ingredient which was used all the way was this idea of artificial synergy synthesis, saying we focus on a few degrees of freedom, and especially on the motion of the center of mass. And all the rest can be solved externally. It's another problem, and most of the time it just works well. And then then we know what we want to do, how to do it, then we use Model Predictive Control and different options. And you can see that all robots I mentioned use that. Then what about Boston Dynamics? This robot, which is one of the most impressive. Well, Toyota published some of their ideas, Honda published some of their ideas. Obviously, they don't publish all their ideas, they have their secrets. Boston Dynamics, they don't publish any. So, we only have hearsay. We know what Mark Rebert was doing in the 80s and 90s. We can see how it relates to what's there. We can discuss with those guys and they tell us a few things. And the general idea is that they do similar things to what you have seen. There is no magic. There is no great idea that nobody ever had behind there. But then they have wonderful hardware. And okay, that's not related to balance. Okay, so last slide and then we can go for a break. What if you don't want or don't have computing resources? For example, what happened in the leg lab in MIT beginning of the 80s, don't have big CPUs at the time. You can't solve a QP or an optimization problem like that so fast. How do you do? Well, you combine simple rules. So you have those robots, as you can see, they were mostly jumping. So you have one control for the vertical oscillations. You have one control for the upper V attitude. Okay. And then you have a control of the state placement. And of course, that was the key to the long-term stability. But this was done every time with very simple P control, linear control. You just have a linear control of vertical oscillation, linear control of the attitude, and linear control of state placement, which was using, in fact, a simple analysis of the special dynamics. They found what they call the neutral position, which is if you put your foot there in the beginning of a stance, then you will end up with the same speed as you began. So neutral position because you don't change your speed. And then from this neutral position, you just adapt with a linear law. If you put your foot position a little bit on the left, then you will go more on the right, or a bit behind and you go forward, and things like that. It's a very simple movement. Similar thing here. What if you want to go biomimetic? Then people say, well, you know, I want to see how biological systems work. So I will use central pattern generators, CPGs, which are oscillators. So you just generate a motion, an oscillatory motion, and then you want to stabilize it. And what do people do? They control upper body attitude, and mostly adapt step placement, with always the same simple linear rule. So the point here is that you can see that it's not very important what you do with your global motion. On the Hugo robot, they even tune by hand the walking motion. Okay? Because that's not that important, what the whole body motion is. What's important is then that you have some simple rule to stabilize, and especially so either stabilize the motion of the center of mass with respect to the foot position, or choose the foot position with respect to the motion of the center of mass. So either you move your feet or you move the center of mass, but you use those two things, and that's it. And you can only use simple rules. So however, of course, since he was using, or people are using separate rules, which are then combined, the end result is sometimes shaky, not optimal. So that's why I think, so most people now don't do those things and use the other optimization scheme based, optimization-based scheme that I showed, because they are more integrated and you have better results like vision feedback, smooth vision feedback. So after all that, I think I told you everything I know, or mostly, and the rest you can find in the written notes about how people generate dynamic walking motions on robots today. Okay, I can't tell you anything more. Then, of course, you see that there is room for improvement, and it's up to you. And so I propose that we make a break now, maybe, and then we'll speak. The second part will be maybe shorter, so that we end up at 12 anyway. So a little bit about motion force control, and then numerical implementation. How do you really program those things on the robots? Okay.
very interested in movements of works, incline, multi-tilted, focus on kind of aspect of the assumptions of equation, very different from how a human say we should try to mimic humans, conceivabilities of characteristics ahead. What's that smell?
Is going to be shorter. I'm going to speak about motion force control very quickly. To be quick and easy. And then numerical details, of course, then we'll go into mathematical details. So there will be a few equations there. I thought that I would begin with asking if you have questions about the first part, but maybe I was told maybe it's better to keep all the questions to the end. So I will continue my speaking for 30, 40 minutes, and then have plenty of time for questions if you have questions. So motion and force control. So far we saw how to generate motion, we saw how this generation can remain online and still generate stable motions, but how do you realize them on the robot? So first thing, of course, you have not only have motion at the center of mass, you have full body motion. So for full body motion, you have a bunch of options, which are standard options that you have in the robots. And so here, I'm not going to spend more than one slide on this, because this is what you find in many textbooks. Of course, what you want to control, as we saw, is control the motion of the center of mass. You want to control the motion of the feet. That's at least what you need for balance. Then maybe you're interested in motion of the hands if you want to grasp things, motion of the head if you want to look at things. But mostly you want to control the motion of your robot in the Cartesian space. So that means that you need some form of inverse kinematics before doing joint control. So that's one option. One option is that once you know the motion in Cartesian space, you just first do inverse kinematics, then that gives you joint motion, the corresponding joint motion will be joint motion. So another approach which was proposed at MIT lab at some time, but didn't get much traction because it was not that much interesting with two options, which was called virtual model control. So you can find some papers by Pierre-Brice. So deciding that you have some virtual models. So if you want to control the height, what you do is that in fact you have a virtual spring controlling the height of your center of mass and things like that. So that was the idea. But in fact you have much more advanced options, competing options, which are the task function approach, which is some sort of inverse dynamics. So you take into account the whole dynamics of your system, then you say what are the different kinematic tasks that you want to realize, then you set up your controller in the task space, and then you compute your dynamics, your dynamic control network. And then you have the operational space control, which is a different view on the same kind of systems. This one was proposed by Cathy in Stanford University. And this one was proposed by French researchers. The good thing about those two approaches, with respect to the others, is that you can set up a hierarchy between your different tasks. You can say, I want to do those many things, I want to control the hands, the head, the body, and the legs, the feet, and the center of mass, and say that some things are more important than others. If you cannot do all those things, then focus first on those things. So putting a hierarchy. And that's especially interesting for walking robots, because as we saw, the motion of the center of mass and the motion of the feet are most important for balance. And then maybe if you cannot look in the right direction, it's less important than keeping balance. So those two approaches are very often used for walking units. So now, how do you control COM motion? So remember, this was the picture of the dynamics when you forget about the angular momentum and then focus on the capture point. So you have the center of mass, the capture point, the center of pressure. So what if we want to control the center of mass to go in a specific position? Well, we know that the center of mass is always going into the direction of the capture point. So if you want the center of mass to go to a specific position, let's put the capture point in this position. And then we know that the capture point is going away from the center of pressure. So if we want, for example, the capture point to go here, then we need to put the center of pressure somewhere there. Okay? So of course that will depend on where are your different feet on the ground. But basically, if you want to, since you push the capture point away from the center of pressure, you must have, if you want to put it in some direction, you have to put the center of pressure in mind. And that's basically what you do with the equations. So that was the corresponding dynamics. The first order dynamics which is convergent, and here which is divergent. The center of mass converging towards the capture point. The capture point diverging away from the center of pressure. And basically, this is the kind of control that you can use. You say, if I want to go to this reference position for the center of mass, I see where is my capture point with respect to this reference. So I go away from this reference with a factor k which is greater than 1. And this is where I put my center of pressure. Okay, so if my desired position for center of mass is here, I take this vector here, and I put my center of pressure away, so with a factor greater than 1 away from here. So then I will push in the right direction. So this is this equation with k greater than 1. And of course, if you put this here, you end up with, very simply with this equation, where you can see that if k is greater than 1, then your speed is going to make your capture point converge to your desired position, and then your center of mass is going to follow in converge there. So that's called capture point control. So this is, for example, I think Christian already told you a bit about that, maybe with a different view on that, but that's what they use on the robot in CDR. But in fact, it has been invented elsewhere also in different ways. So Professor Sugihara, I think now he's a professor in Osaka University, he studied in fact different controllers for the center of mass and the center of pressure, which is called the ZMP, and he showed that what he calls the best COM ZMP controller, that's the title of the paper, is in fact this controller. So you can see different researchers having different look at the problem just show that, well, this is the best way to control the motion of the center of mass. Now, what about force control? So the robot, the motion of the robot completely depends on the contact forces. That's what we saw. And the main problem that we have in controlling the forces for walking is that you have oscillations. You can see many oscillations in your robot in many situations. Especially because when you walk, you keep hitting the ground. And every time that introduces oscillations in your system. So the main goal that you have usually for force control is damping. That's usually what people do. You can even see, if you look closely at videos of the Honda robots, or if you look at the videos of the HRP2 robot, or if you know how they are done, you know that they have elastic parts in the ankles so as to dump those oscillations. So it's the main focus of the force controls. But of course, if you introduce dumping, you introduce delay. Okay? With respect to your desired force, you are going to realize your desired force, but with some delay. So what should you do? So some people, like from DLR, Christian Ott, and with his PhD student Johannes Endelsberger, he showed that, well, this controller is robust to some extent with respect to delay in your center of pressure. So this gives you where you should put your center of pressure to control center of mass. But even if you realize this control with some delay, it will still be stable. So one option is to show that, well, it doesn't count much. Another option is to say, well, maybe it doesn't count much, but it counts. So maybe it would be better to take this into account. So just consider that the real position of the center of pressure, so the real position is not exactly the desired one, and because of your controller, you have some delay. So your center of pressure is going to converge to your desired center of pressure, but with some delay. So you do some dynamics like that. And then what you do is that you take the same controller and you add another term here with respect to your current position of your center of pressure, and that gives you your desired position of the center of pressure. So this was proposed by Kajita. This is how they made, for example, this demonstration in 2010. So the HRP4 robot, which is very interesting to see in real life. So walking on the pavement. So here, the walking motion was predefined, and what was tested is this motion stabilizer. So how do you control force and motion so that we see that from an angle that in fact there is an angle here, and here have a real floor with it's noisy, but just showing that this controller, which will decide of where to put the center of pressure, knowing that you have some oscillations here, and then to follow your desired stream. So that's the kind of things that you have. So here the slope was not low. The noise here and the dirt here, which have different damping effects in cinema, are not low, not model, and it's the robustness of the stabilizer. So that's, of course, here you have some controller that gives you where you want to put your center of pressure. What happens if, when you have strong perturbation, you want to put your center of pressure outside of your support plane? Okay, with this equation, that it gives you Z should be here, it's outside your support plane. What should you do? Of course, and that's what people do so far, you can saturate, say, well, okay, I want to put there, but it will stay here, because anyway, my support plane is right here, so it should be put here. And then hope for the best. Okay? So you just saturate your controller and hope that it will work very fine. The other way would be to take into account these constraints. But then that falls back to the constraint dynamics that we were dealing with when generating the walking motion. So in fact, what we should do is not generate walking motions and then realize them with a stabilizer like that, but try to combine those two things together and say, we do the feedback, this kind of feedback, directly in the generation of the motion. And that's what a lot of people are trying to do. That's what we are trying to do with Pierre-Brice and with other colleagues. So people, the team by Kajita, so all HRP2, HRP4, we are trying to combine in a single computation the stabilization and the generation. But so far, you still have a separation between these two things. And because it's still a work in progress. So, once again, I told you almost everything I know about motion force control. And you can see that there's not much here. So maybe there's something I don't know, but of all the robots that exist so far, there's not much more to this, as far as I know. So I propose that we now speak about numerical implementation. So we'll begin by a quote by a famous, I don't know if you know him, but he's famous, He's the guy who invented object-oriented programming. So that's quite something. Alan Kay. He worked at that time in the Xerox Park, so a famous place for computer scientists. And he made this claim. People who are really serious about software should make their own hardware. So I'm not as famous as Alan Kay, but I'm going to borrow his quote. I didn't even do much yet so far. People who are really serious about control algorithms should make their own numerical solver. For exactly the same reason. You need to know what's happening in you, and you need to, if you want to push your software, if you want to push your algorithm, control algorithms further and further, then you will need to tune and modify and make your own underlying technology, hardware or inputs. So, first thing, we have seen that in all those control schemes, one way or another, they compute dynamic motion by solving the equations of motion for some time, for 1 step, 2 steps, 3 steps, and then optimize something. So they work on trajectories, everybody. So of course, we don't work on a continuous trajectory, we work with a discretized trajectory in computer computation. Digital computation. So for example, so in Tokyo University, they say, well, let's sample our trajectory. So between 50 and 100 times. So we have 50 and 100 samples. So knowing that they were considering 3 steps that take with this kind of length of time, so that makes a sample every 50 minutes. So Thomas Buschmann in Munich, he proposed to use cubic splines for 3 steps. So around 100 millisecond period with 20 or 30 pieces of spline. Urisawa, for the HRP2, proposed to use quartic or triptych polynomials piecewise. So other people, so Takenaka, this is for the Asimo robot, they use these pieces of line with exponential parts over 2 steps, so every 70 100 milliseconds for each piece. So Jerry Pratt uses pieces of exponentials. You can see, well, general options like that. So Van de Pan, so that's the graphics option. So in Google Graphics, I showed uses only 2 pieces of cubic spline. Kajita, in his original paper for his LMP preview control, was quite extreme. He was using samples every 5 milliseconds for 2 to 4 steps. So that means 600 pieces for his trajectory. So Henri Hertz was my PhD student, and we just proposed to use pieces that every 100 milliseconds, and pieces with constant jerk, so cubic splines. So basically, what we propose, let's use cubic splines for the motion of a C wave, and we consider splines every 100 milliseconds because you can, of course, so between your control points, your spline is going to vary. And of course, you want to make sure that it doesn't vary too wide. But you can bound the overshoot of what's important, which is the COP. So you can very easily analyze that if you give a maximum value for COP, because that's the limit of your support polygon, then the validation can be bounded with respect to the maximum of center of mass and the square of the sampling period. So then it happens that if you take 1 millisecond, 100 millisecond piece, the overshoot could be a few millimeters, 2 millimeters, something like that, for a human-sized robot, which is what we're referencing. So you just need to take, let's say, 1 centimeter margin within your support polygon, and you're safe. So let's go with cubic splines with control nodes for the spline every 100 milliseconds. Then you do this for length of time which is about 2 steps, so we take 1.5 seconds. So you have 15 parts, pieces in your trajectory. So let's look at detailed formulas, if you want. Nobody complains, so let's go with detailed formulas. Okay, so basically, this is something that you can find in this paper by my PhD student. So if you want to take a nap now, you can find the exact detail from this data. But maybe I can show you. So basically, what we do, we have n steps in our prediction. Okay, so we compute the prediction for the next n sampling periods. So we said cubic splines. Cubic splines can be represented in different ways. One way is to say I have control positions for my n steps. Another way, the way we chose, is to say that it's in fact a piecewise third order polynomial with constant third derivative, so constant jerk. I'm going to tell you later why we make this choice. So basically, the value that we want to find is the third derivative of the jerk. That's how it works in English. The jerk of the center of mass for every sampling period, for the next n sampling periods. Okay? So we put this in a vector, x and y coordinates. So that's what we want to find. And depending on this, of course, you can integrate your dynamics. Here you have the third derivative, you can integrate the second derivative, you can integrate the first derivative, and then you have the motion position. So here, if you say that you have the speed of the center of mass for the next n sampling periods, they will depend on this vector here of jerk, with some matrix here, and it will depend on the initial state of some matrix here, linear. You can say the same for example, a linear combination of position and acceleration of the center of mass. For example, the center of pressure, which is a linear combination of position and acceleration. Acceleration is a linear function of this. Position is a linear function of this. So you end up saying the position of the center of pressure for the next n steps, which I put in this vector, is in fact a linear function of this jerk of the n steps, with this matrix, and then, depending on the initial state, so the current state, position is linear acceleration of the center of mass. So you have these. And if you want the exact formulas for this, these are just for integrating dynamical system. So you have such simple matrices. And if you are interested, you can do an exercise later to write this, but usually, I just give the paper to my new students, that's the result usually. However, so in the paper, there is one trick. So there is one mistake, and so you have to correct it. That's part of the exercise. But anyway, so you have those formulas that you can apply. So then, we have a function that we want to minimize. So I showed you that, for example, we want to minimize so you have the speed so here, this is a vector with the x and y speed of the center of mass for all the next n sampling periods. I want to follow as much as possible a given reference. Maybe it's interesting to still minimize the third derivative, and it proved to be interesting. So in fact, in this paper, we analyze this paper here. So that's the Robotics Society of Japan journal, which is called Autonomous Robots. Here. So if you only want to track speed as much as possible, you will have some oscillations in the motion of your center of mass. Small oscillations in the speed. So here it's just like adding some damping so that you have a smoother result. So it's not very important, but it helps having a smoother result. Here, you can also add another term, which is, well, why not anyway try to keep the center of pressure not too far from the middle of the foot. It always helps for robustness. Okay. So we have this function that we want to minimize. Now, the position of the feet in the next n something periods is not fixed. So if you take the position of the feet for the next something period, so you take the current position of the foot on the ground. So this foot cannot move. It's on the ground, it's fixed there. So for the next few something periods, the position of the foot on the ground is this position. So you have one here. And then after some time, for some something periods, it will be the next step. And then for some time it will be the next step. And then for some time it will be the next step, etc. So here you have, in this vector here, the next few steps. So the next 1, 2, 3 steps, which are free variable in our problem. Okay, so we want to solve this kind of thing. So we have these matrices, additional matrices that we introduce. And the variable that we want to find are the jerk of the center of mass, which will give us the motion of the center of mass, and the position of the feet on the next steps. And of course, here we can reply, so this is directly the variable that we find. Here we saw that this is a linear function of this variable. And here we saw that this is a linear function of this variable. And this is a linear function of this variable. So we have, in fact, a sum of squares of linear function. So this is a quadratic function. And you can express it, the standard way to express a quadratic function is in expressing it in this form. So here you have a Hessian matrix that you multiply on the right and the left by a variable. And here you have a linear term. So here I don't describe a linear term, it's just follow the same rules. I just describe how you obtain this matrix. So what we have is this function. And basically you have the same function in x and y. These are orthogonal directions for this function, they are independent. So in fact you have a matrix which is of this form with 2 times the same matrix on the diagonal. So then in xk, what is our working variable? It will be the acceleration, the jerk in x and y coordinates, and the next footsteps in x and y coordinates. And then you just replace here these equations, this one and these ones. And then by just recombining things, you obtain this kind of matrix. Okay? That's not too hard algebra. I mean, that's some standard algebra. You just recombine things, rewrite things, and you just end up saying, well, what I want to minimize is this. And this means following a given trajectory, minimizing also the jerk, and keeping the center of pressure not too far from the center. Then we have constraints. You have constraints on the center of pressure. Okay? So I have the center of pressure. I have the center of the foot on the ground for the next n something periods. Then if I just reorient, so here it's the orientation of the foot on the ground. And here suppose that this is given in this stage. If you want to deal with it, then there are ways to deal with it, which are described in the paper, but I thought it was enough maths for today. So we suppose this is given. So you have the rotation matrix. So depending on the orientation of your foot, it gives you, this gives you the position of the center of pressure with respect to the center of the foot in the local frame of the foot. And then if you consider that you have rectangular feet, you bound it by upper and lower values in x and y coordinates. So you have a constraint of this form. And once again, well, these and these are linear function of the working variable that you want to find. So you can write them as a linear equation. Okay? So what we want to do is minimize this quadratic function with these linear constraints. And that's what we call a quadratic program. So then we want to solve this quadratic program. But there is an interesting trick that we can do here. We can observe that, in fact, this constraint here can be made trivial by just making a change of variable. Because, so let's consider that you have this variable instead. This variable, which is, so the position of the center of pressure. So this is the position of the center of pressure with respect to the center of the feet in the local frame of the feet. And we can make this change of variable because we can see here that those matrices that we have are full rank, triangular, invertible. So we have a one-to-one correspondence between the jerk of the center of mass and the position of the center of pressure in the local frame of the feet on the ground. So we have a one-to-one relation, so we can make this change of variable. By working with this variable instead of the jerk of the center of mass, the nice thing is that this constraint is made trivial. It's just that Z prime is between L and U. And we see that this makes a big difference.
I just have one point. Why is there a lower bound on the difference between the 0, 1 point and the center of the foot?
Well, it's just to say that in X coordinate and in Y coordinate, or X and Y, it cannot go, so that's the two boundaries of your feet.
Oh, the other direction, yeah.
So, how do we solve a quadratic program? And we have to go into these details to really understand what's happening. So, in case we don't have any constraints, we want to minimize this quadratic function. Do you know how you define what is the optimum function? So please, somebody raise your hand. Tell me how.
Actually, the maximum or minimum, then
Yes. So how do you define the minimum or maximum? So the
derivatives. Yeah. I take the derivatives.
Yes. So the minimum or the maximum for a stationary point in the general case, but here we have a complex function, so it's a minimum, is the point where the derivative is 0. Okay. So that's what we do. In order to find the minimum here, the easiest way is to say, let's find where the gradient, where the derivative is equal to 0. The derivative of this is this. So that's a nice thing about quadratic functions. You can find a minimum by just solving a linear equation. So, I mean, it's hard to be a simple problem to solve. You have to solve a system of linear equations. Moreover, this matrix Q that we have here is mostly constant. All these things here are constant. Only these parts are changing. And that's by 1/10 of the matrix. So it means that you can already pre-compute most of what you need to solve this in the system. I was not sure, but finally I decided I would skip the exact detail how you solve this. But basically, so make a factorization of this matrix Q. And the thing is that since most of it is already known, most of the factorization is already known. So really you can pre-process most of the computations here. What happens when you have equality constraints? So when you want to minimize the same function, but now you have a constraint that ax plus b is equal to 0. Linear constraint. So we know that the minimum of this function is where the gradient is 0. But most probably the point where the gradient is 0 does not satisfy this constraint. It's not in this subspace. So in this case, we're not looking at the point where the gradient is 0, but the point where the gradient is orthogonal to my constraint. Okay, so how do you do that? Usually you do that by introducing what's called Lagrange multipliers. So if you don't know anything about that, just trust me. You open a book on numerical optimization, that's second chapter. First chapter is this, second chapter is that. So you introduce Lagrange multipliers, to use the transpose of this matrix. So what you need to find is a couple of values, x and lambda, such that you solve both. You are on this constraint, and you find that the gradient is orthogonal to this constraint. You can rearrange this, you can just group those two equations in this way. And then you can observe, you can prove that if your problem is complex, so if your matrix Q is invertible in nicely behaves, and if your constraints are nicely behave as well, in the sense that they are full rock. So that's fixed to you. Anyway, you know that this is invertible, this matrix is invertible, so you know that there is a unique solution in this case. So if the problem is convex and everything is fine, you have a unique solution to this system. Okay, so solving this equation gives you the minimum of the constraint problem. So once again, what you need to do is just solve a system of linear equations. So you can observe, however, that with respect to the previous equation that we need to solve, this one is a bit bigger. So it costs more to solve. There is one option higher. What if the constraint is trivial? What if the constraint is, well, x plus b is equal to 0? Some x, some selection of x. So some of my variables, I fix them to some given values. So the selection, I use it by mentioning this underscore. I don't know how to. Or you can use it, in fact, by saying I have a matrix E, but which is trivial, with only zeros and ones. Just selecting some variables, and those variables are fixed. So you could, of course, use the same Lagrange multiplier as before. But in fact, since here this matrix is trivial with zeros and ones, this just means that for these lines here, lambda is equal to what happens here, and so that's not very interesting. And in fact, it's the other equations which are equal to 0. So what happens in fact here, what I should do is just, I have fixed some variables. Fine. This part of the problem is already solved. I know those variables. So now I just select the remaining variables, extract from my matrix Q the columns and the rows which were corresponding to the values that are already in there. Just take them out of the problem, and I solve this set of equations, which is smaller. It's just it. You fix some variables, you have a smaller problem with the remaining variables to solve. So here you can see that in case the constraints are trivial, having constraints help me solve my problem faster. It's a small problem, faster to solve. So that's why here it's very interesting to make this change of variable. Because, as I mentioned, the first proposition by Kajita in the ZP control, he had only this function that he was minimizing. Because he said that's fast to solve. Solving this amounts to solving this linear equation. And I can pre-compute my inverse of matrix Q, and that's fine. Then I just have to make a matrix vector multiplication, or I can even go faster and find the solution. But you see here that introducing constraints, but making them trivial, can help you solve the problem even faster. The problem, however, is that here I was speaking about equality constraints. What if I have inequalities? So, and I'm sorry, I never managed to find a good way to introduce this. But, so we'll have to draw things in the air with my hands and try to help you understand. When you have, when you have an inequality constraint. So here, I was saying, how do you find the minimum in this constraint? Most probably the place where the gradient 0 is not on this constraint. Now you have an inequality constraint. I mean, so my value of x should be less than something or more than something. So I have one chance out of 2 that the point here is on the right side, the correct side. Okay, so in some situations, the inequality doesn't change anything to my solution. It's the minimum. The minimum satisfies inequality. So it's just as if it was not here. In the other case, then I'm stuck on the inequality. So if I'm stuck on the inequality, then it holds as an inequality. Okay, so I just say, I'm on this inequality, and then solve this system. So in fact, the whole process of solving a QP with inequality constraints amounts to finding which are the active constraints. How do we know which constraints hold as equalities and which one we just don't care about? And that's where normally you need an iterative process. So here you just need to try. You try, are these, if I activate those constraints, so do I have a solution? Yes, no, and then you just do it. The point is that, look at this. This is, so this is time. This is time, I mean real time in my experiments. So, so it's so it's counted as number of sampling periods. Just to avoid that this is wrongly worded. So first sampling period, second, etc., 50 sampling period. And here you have the prediction horizon. So meaning that here it's the current time, and then this is further and further in the future. And here, what is plotted here is what are the active constraints. So meaning, in this equation here, the lower and upper bound of the center of pressure, the NaoQi, which one are active? So you can see the first thing, which should look obvious in some way. You have a pattern, and this pattern is that when you progress in time, the active constraints go closer and closer to your current position. So it's just here sliding in time. But what's important is also that, well, okay, you slide in time, but it's always the same constraints which are active, and the same constraints which are inactive. The point is that if you want to solve a single QP, you need an iterative process to find which are the active constraints. But here we solve a sequence of QPs. At every sampling period, we solve another QP. But this other QP is very similar to the previous one, which was very similar to the previous one. And in fact, we can make a good guess about what is going to be the next active set. Just look at what happened before, just the previous step, and just guess. And if you make the right guess, you have no iteration at all to make, if you have the exact guess. Then if you are slightly off, you need one or two iterations. And that's what we observe. But you really don't need much more than one or two iterations more, and most of the time just no iteration. So, and here you can see, for example, there is a disturbance happening here. So here push the robot. So then you have suddenly a lot of constraints activated, but then they go nice part. So it means that solving a quadratic program with inequality constraints, but if we have such a nice behavior, time behavior of the QP, then it's not much more costly than solving a QP with equality constraints. And if my equality constraints happen to be trivial constraints, it's even faster to solve than a QP without constraints. So my colleagues, when I proposed to introduce inequality constraints so the dynamic constraints on the COP, they told me it will cost a lot to compute. I thought, no, it will be faster to solve. And you can see that, because if the COP is on the boundary, then it's fixed. Then I don't have to compute this one. It's less variables in my problem. Very good.
So I have one question about this. So you can predict which ones are going to be the active constraints, but can you be sure that this is the optimal solution then?
No. Then you check. So you make this guess.
Yeah.
You check. And then you apply the standard method. So you check if it's optimal. If it's not optimal, what should you do? Should you activate one more constraint, or should you deactivate one constraint? And then you make your iterations. You see? So I will We will speak about more in the next slide about this. So the idea is that, in fact, this is a very standard feature that you have in advanced QP solvers. Standard QP solvers, just give them your matrices and they solve it. Advanced ones, we can tell them, and this is my guess of the electric constraints. And they are made to take this into account and then iterate if necessary. So here you have computation time on the CPU of the HRP2, which is the core 2 duos rather than A2. So this is for the standard QP solver. And you can see it takes 40 milliseconds to solve. And you can see that the computation time varies. In fact, it varies depending on the number of iterations that we need. Then we began playing with the solver, and in fact, designing our own solver. And so first thing is, so here we couldn't, so we gave the matrices to the QP solver. First thing that we can gain some time by pre-computing a few things. So as I told you, this matrix Q is already fixed for the most part, so you can pre-compute things. So you can gain this constant thing that you pre-computed. And then comes the fact that, well, we can delete most of the iterations by using the previous active set as a guess for the current one. And then you have these things. So you have nearly, zero. So here it's less, it's a fraction of the same. And we have improved now and more of the code. So, and then sometimes you make one iteration, 0, 1, 2, 3, 0. And then sometimes you have some peaks, of course, because here you have suddenly many constraints which need to be iterated at that time. But then we propose another thing, which is a quite standard idea in fact. Well, of course, let's put a limit on the computation time. Let's say that we just fix to 2 milliseconds or 2 iterations, okay? Maximum 2 iterations. So what happens is that we stop at the suboptimal point. But you can choose to have a specific algorithm here so that you stop at the suboptimal point, but which satisfies all your constraints. So you are sure that all your physical constraints are satisfied. It's only that you are not making the best choice. And the point is that, so you see what happens if you need to activate many constraints at once, you will activate only 2. But the next something period, you will activate 2 more. So you take some delay in finding the proper active set, but you will converge very quickly. So it's just a matter of finding how many iterations you allow with respect to how many activations happen, but the mean value for this bit of statistics here. But it's quite straightforward. Usually you do not need more than 1 or 2 iterations to converge very quickly to our system. So here you have some results we had a few years ago here. Just mentioning that we also do this for full body motion control. So if you want to control a full body, but then you want to put inequalities on that, then you solve a QP, and you have the same things. And the statistics is that 97% of the time you don't do any iteration, and the remaining 2.99% with only 1 iteration. So you have that's an important message to take home, is that you shouldn't be afraid of inequality constraints, and there are good solutions.
What is, in the previous slide, what is the meaning of the double line?
So in fact here, you have the indices of the constraints. So you have the constraints in X and Y and upper and lower constraints. So in fact you can see that, so here for one period you had 2 constraints which were activated, and then the same 2 constraints activated.
And when it goes up to 0, which is like the
current time,
then it drops back down.
No. In fact, you can see that it's not exactly synchronized. In fact, this is the end of your horizon. This is the beginning of your horizon. So if they are synchronized with respect to your steps, of course, when you finish a step, it means that you are beginning a step there. So then you will have the exact matching, but here it was not matching exactly. Yes, so let me stop here. It's 12, so we can have time for discussion. So basically, I wanted to show you, so those things are things that we tested on the HRP2 robot, and things that work every day on the HRP2. And things that Aldebaran is currently porting, so checking and adapting to the Nao robot. But this time they go from our solver instead of reinventing everything from scratch. And so this solver is available on in open source online already. So you can, if you check for, I will give you the details. It's called MPC WorkGen, and you search for it on GitHub and you find it. In fact, if you find the Aldebaran Robotics webpage on GitHub, then you will find it there. I don't recommend that you go look at it now, because it's still a work in progress, so you are going to waste time. But just wishing that it's already there, and they commit, so students there are committing every week or so, and it's going to stabilize soon. And then we have full access to an implementation such as this one. So implementation of these equations for this scheme, with further tricks on true computation of the matrix and everything like that. So then you can see how it's done, and this will be the one that's now on all other prototypes of Aldebaran Robotics. And yes, but here I was mentioned, I'm insisting on an important message is that if you go into the details of your numerical solver, you can be much more clever. If you don't know about these things about the QPs, then the common knowledge, ask anybody. They tell you that it takes time. You know, many iterations, and you don't know how much time because it varies. You know, and so you should avoid using this for your robot control. Whereas you see, when you're clever enough, you can be very fast, and as I claim, even faster than if you want to. So I hope that I convinced you on this.
Could I ask you some more about the implementation though? Because if I were to do something like this, then like did you implement this in MATLAB and use under the MATLAB matrix and inverse calculations? Because I would be extremely concerned about numerical stability, which I'm not an expert in, and there's many pitfalls from what I understand. So that's just in adding two numbers correctly together. So.
And that's a problem with MATLAB, which is, so if you have a problem for robustness, you shouldn't use MATLAB.
Okay. That was my only solution.
Okay, no, sorry, but that's, so for example, you have QP solvers in MATLAB, it's called Quadratic. Okay. So, of course, so, no, so let me state it differently. So, one of my PhD students, current PhD students, so far he's implementing new ideas about all this. So he didn't want to work with the C++ code which is used now in Aldebaran and HRP2. So he started with fresh implementation, not in MATLAB but in Octave. So yes, what he began with is just coding this matrix and then sending it to the QP solver of Octave. But then the QP solver of Octave happens to be not reliable for some reason. So we know all the QP solvers. There are some which are freely available. If you want the better ones, of course, you have to pay for them. One of the very good ones is proposed by Stanford University. There's a huge group in optimization theory there. But you have to pay for it. I think it's $700 for it. It's a very good one, and it allows right from the beginning, it gives you a possibility to have all stars. So to give, this is my guess. So the only thing you have to do is use this software, which is called in Fortran. So you need a Fortran compiler, and then link to Fortran code. But once you have that, you just feed the matrices, gives you the result, and that's it. It works without any further hassle. So as soon as you have reliable QP solver, everything is standard. So matrix computations are not ill-conditioned, so there's no trouble there. It's just
no, I mean, I understand that part, and I totally agree. If you understand your matrices, and you can do some of the factorization early or Forster. I was just more concerned about whether you actually brought it all the way down to a C++ code, or whether you used some properly debugged and implemented matrix libraries, or even a 2D solver in itself. That's all.
So we do use reliable software. I mean, you have reliable software in C++ for solving QPs. C++ or Fortran, interest more. But and for doing linear algebra, so matrix factorization. But let me insist that at least in this situation, these QPs that I showed, the ones that we saw, they are very well detailed, well conditioned, so that even if you just use textbooks method, for example, for solving the problem, you need a Cholesky decomposition. Just Wikipedia, Cholesky, you have the algorithm, you code it in C, and it should work. Because this works in the standard case. Of course, if you are a nasty case in condition, then you need proper software. But this works in the standard case, and hopefully this is a standard case. So yeah, you don't need much more. The important thing here is the QP solver. And this takes time to code by yourself. This needs very precise knowledge. So on this, you should use already available software. But unfortunately, you do not trust every software. I told you in Octave, and one of my postdocs, I never use MATLAB, one of my postdocs told me that even when MATLAB is sometimes you can't trust it. So just to let you know that, so my PhD student in Octave, he began by just coding these matrices here, and then sending to a QP solver, and it didn't work. So, well, we just linked an external QP solver, and it works. And so Sven asked me if I could propose some exercises. And I thought about, so there's this Octave code, which is freely available. If you're interested, just ask me, and I will give you a GitHub page of my PhD student, and you can download it. But the point is that it can be used with fresh implementation of Octave, because you need this additional QP solver. So we finally decided it was too complex to set up as an exercise today. But basically, you take this open source QP solver from colleagues, link it properly, install it, link it, use it in Octave, and then you have the simulations of walking. Well, you don't have the simulation of a full robot, but you can see the feet in the zero motion. Working. And if you want the more involved C++ implementation, as I said, it is readily available, maybe not very useful, very helpful so far because it's still work in progress, but it already works. So you can also see, in fact, we use the Eigen library for linear algebra. And for the QP solver, you can see exactly the exact QP solver we are using so far, because we are developing our own, but so far we're using the multi-shell solver. So you can see those things if you are interested in wasting time. Are there other questions? Now I think it's time for questions. Or was it all clear? Or you are all too tired?
So you made the assumption that the robot would stop within maybe 2 steps in some capture point. but is it also possible to define like a similar, like generalized point where the robot would move with a certain desired speed?
Okay, so yes, you told me you were going to ask this question. So basically, just mentioning that what you thinking about is what Mark Rebels was doing with neutral position, as far as I understand, which means so if you don't want to stop in 2 steps, but want to keep the current speed. Okay. So that's what he called a neutral position. This neutral position, you can compute it with analytical formulas in simple cases. Okay. However, for so that's what Rebels was doing for his robots. Now, of course, this capture point here is only for stopping. So, do we have an analytical formula for when you don't want to stop but want to continue with the same speed? The answer is no. We don't have the analytical formula. So, well, it doesn't mean that you can't find it. Nobody looked for it. So here I mentioned the capture point for stopping in 1 step. You have a recent paper by Pierre-Brice and all his colleagues, in the 2-part paper in the International Robotics Research, which is a fabulous paper, which just compute the capture point for more complex models and then for many steps. So you have further developments of this idea, but not the one that you want. However, this is solved usually numerically. So, for example, the Asimov scheme here, which you see, so the capture point is decided to be put in some position. How is this reference computed? In fact, they compute it so that they have a constant speed. So if you look at the paper by Takenaka in ICRA 2010, I think, 2009, you have the reference in the paper. Basically, they impose this goal. They say, well, I don't want to stop in 2 steps, I want to be in a cycle in 2 steps. Because I know that this is viable. It's not capturable, it's viable. And they then decide about where to put the C reference into some general rules and solving equations. So the idea is, my idea about that, as you can see, is I prefer to focus on numerical computation. Just put the whole equation, say where you want to go, that's it. I believe that so it can be more expensive to compute than if you have the exact analytical formula. But it's so much more flexible, and you can expand on it. See, if you want the analytical formula, you can use in some specific case. In the numerical case here, I was not considering the angular momentum, but I show you that some people consider it. Well, it's just a matter of adding this new term, you know. And people now are combining this with hand grasping, so that you can take into account the grasping force and maybe the compliance directly in your MPC for the balance, so you can then anticipate on your manipulation task for your balance and things like that. So these numerical schemes can be expanded to more general cases. So that's why I would advocate for this, instead of looking for the exact analytical solution for this specific case. And I believe CPUs now, computers can compute all this. It's not a problem. It was a problem 20 years ago. So I believe yes, we shouldn't spend too much time on this. Although, as I said, this introduction of the capture point was brilliant. We didn't need it. I mean, at the time when he introduced that, Kashida was already making his robots work with the MPC scheme without terminal constraint. So we didn't need this to make robots work. But it helps us understand a lot of things. It's very helpful.
When I look at this passive walker that Jackie brought, or there are also versions that walk on level ground with some powering, but they are mostly governed by sort of the natural dynamics. So not only of this inverted pendulum of the center of mass, but also by the hanging pendulum of the swing leg. And to me, this looks much more natural in some way than maybe the HRP4 walking. So when you show this, the HRP4, of course, this is very impressive that the robot doesn't know the disturbances of the stone and maybe the tilt, but still it looks like, very much like a robot walking and not being governed by any natural dynamics of the system. So, is there any way to combine the two things? So obviously we want a little bit more control than in these passive walkers, but on the other hand, it's supposed to be energy efficient and maybe elegant and whatsoever. So, what's your thoughts about how to get the best of the two worlds?
So in fact, it's part of it should be part of this chapter, but not in this extract. So this chapter, I'm working on this with Russ Dedrick, who has been working on more natural walking. So, and that's the next section. Here you have, I think it stops at section 4. And then the next section is more efficient walking. So I believe, there are a lot of misconceptions. So here I show you a couple of misconceptions, but pendulum is not just a pendulum. Inequality constraints, should be afraid of them. Another misconception is, why do those robots walk like robots? Okay. There are many reasons why. So, of course, you had a serious problem in the 80s and 90s that you had predefined footsteps, and that limited, of course, the possibility to push or to react. But as I try to convince you, this is something that we know how to solve now. But you can see that this has been solved, and still the robot walk like robots. Because that's not, so the problem is absolutely not to have dynamic motion. This is dynamic walking. The problem is related, so you have actuators, they use position control motors, so not force control, so this means they have very bad constraints on how dynamic your motion can be. So they have constraints like that. So stabilizing the force, that's the most important thing, is controlling the contact force, because contact forces are what drive the robot. And they have tremendous problem with that. But then, so far, most of them, they use inverse kinematics, and you want to go freely over kinematic singularities, but we don't know yet how to do these things properly. So you see, the problem in walking like a robot, in my opinion, comes from various problems, but those problems are not not related to walking itself. It's more like robots today move like robots, not only human robots. Moving like a robot so far is making all the robots move like that. So it's not the problem. The problem is not there. Now, as we know, the best way to adapt to perturbations is by making a step. It's not by trying to fight against the perturbation. You are very limited. Either by using a center of mass, but then if you push enough, then you are going to go in this direction anyway. It's not by moving your arms, so which will help you with the momentum, but this is very limited. We know that the best way is to make steps. And we know that the best way is to make fast steps. So you need fast control. We discussed this earlier, fast motors and things like that. But we know that fluid positioning is very important. And of course, you have the dynamics of your system, the internal dynamics of your system. And these dynamics can be tuned to naturally find the proper step. And this is what you have with those passive inequalities. If they are stable under with certain initial conditions, it means that the dynamics drives the foot position to the, if it goes a bit faster, then the foot goes a bit further, so it slows down. So and then you converge to a constant speed. So that's related to tuning the mechanics, so designing the mechanics, and that's something which so far we're not ready to tackle in a serious way. So you have a lot of people design humanoid robots out of, it's a technological challenge. The HRP2 or 4, they look human. They don't have the dynamics of the human, the masses, so it doesn't match. So some people try to match the dynamics of humans, saying, that works, let's copy it, and we'll think later. Thinking that, well, maybe if this dynamics is well tuned, then maybe it will behave like one problem there, however, is friction. This is a huge problem in control of robots. So you have to compensate for friction, so you have to add energy to the system anyway. But basically, for me, the next step, where do those threads converge between passive dynamic workers and those full-fledged human robots, which can do many more things, but in more rigid way so far, is in, so you have things to do outside of the strict realm of leg locomotion, which are better actuators, better motion and force control, those things to have more natural motion for robots anyway. So this needs to be done. Compliant motion and things like that are still research for manipulator robots. So you need this, and then you need better mechanical design. And I think this will be the convergence. I believe there will be a convergence.
Yeah. What about springs? So, Boris Maus, for example, in his models, the legs always look very springy, like a linear spring. And yeah, we had also on Tuesday 2 talks about compliant actuation by Nikos. We talked about fixed compliance or also variable compliance actuators, and there was the Japanese robots with muscle-like actuators that are very compliant. So what's your thought about compliant robots?
So I've been working on walking robots for 17 years. It's been 15 years that I keep hearing the question, so what about springs? We all know that biological systems, animals and humans have springy elements which store energy, and that would be the best way to go. But then the next thing is, well, okay, fine, we all agree. We need to put springs somewhere, somehow, and use them somehow. But then that's the beginning of the problem. So in 15 years that I know mechanical robot designers, they tell me you should use spring. I can design your robot with spring, and I tell them, no, I don't want. I will be unable to control it and use it. Personally, I don't have the knowledge. So people in TLR from Portis and out, they have been working for more than a decade on controlling robotic systems with springs. Okay, so and then maybe in a few years they will be able to use it efficiently for walking. Maybe in a few years. Their robot here has springs. The Toro robot has actuators with springs, but they don't use them so far for storing energy. And in fact, their robot is position control as far as I know. So they have an advanced actuation system, but they don't use it in the way we would love to see it used. So using springs to store energy. So I mean, we have all been convinced, all the people, you know, so the designer of the HRP2 and HRP4 is far from idiot. He's a wonderful roboticist, I can tell you. He knows everything about all that. But he has to make a choice today. What's the current technology if I want a human robot to work today? Okay? So one thing is to say what we should do, what we should look for in 20 years. But today, the technology, the only technology that we know how to use to make a robot walk is this one. And nobody's happy with it. But that's, you know, what we should, everybody agrees that's what we should do. And you can see that it's only now that you have viable impedance actuators, and so trying to store energy and reduce it later. Because using only springs, how do you produce really actuators that you have the series elastic actuators, which were proposed, I don't know, 15 years ago in the MIT lab. Well, not many robots use them so far. So people were waiting for viable impedance actuators. They are coming. Maybe so in Geneva they tried to use them, but so far so good. But so far no robots knows how to use that. But we all agree that this will be the future. We are all eager. So personally, I can't work on everything. So I wait for people in DLR who work on the viable impedance actuators to one day solve these problems that we can use it.
But I think that Mark Wieber in the 80s of the previous century, at least for like running and hopping, he knew that of course their springs are even more important.
Yes. Yes, but he was focusing on a very specific problem. He had very specific design for a very specific problem. You can observe that he was, for a long time, only working on jumping and running robots, not walking.
Yeah.
The funny thing is that the first reaction of a lot of people is that, well, running is harder than walking. So if you know how to run, you should know how to walk. That's the general conception, which is completely wrong. It's very funny that you can even observe it among humans. It was measured. You have humans walk on a treadmill or run on a treadmill. And then you perturbate their CPU. So you make them do small numerical tasks, multiplications and things like that. So the brain is occupied with something else. And then you perturbate. And you can observe that running is much more stable than walking. It's much easier to keep your balance. While running, you need much less brain power to run and to walk. That's as you measure in humans. And that's what we have observed also on robots. And that's the reason why I had running, then running robots before then we walking robots. So, Mark Wieber was the results are impressive, but they're impressive because he was so clever that he chose the easiest thing to do. And then if later you want your robot to not just run around, but you want it to get your beer and bring it to you and not shake it, then he can't do that.
Yeah, but like Pican, André Seifert, and Moritz Maus, they apply these springy leg models also to walking, so they are not completely satisfied with that yet.
Yes, but it arrived 15 years later.
Yeah.
It was only in the 90s, 15 years after Mark Wieber was making those run, that they, even in MIT, they took 15 years to begin to have walking robots. So it's much harder, that's one thing. And then, what I agree, so springy legs are the thing that we have to know how to use now. That's the next thing that we need to understand, how to use them. But I mean, use them on real robots, not in simulations of biomechanical systems.
Yeah.
And yeah, so we need to do that. And if nobody did that so far, it's not because nobody thought about that. It's because people don't know how to do that. So it's easy when you focus on the simple problem of you have your biomechanical model and you simulate it, and yet it needs a lot of tuning. It's easy if what you want is just a robot. It's easy, of course. It's easy to say that it's easy. It needs a lot of tuning, but it's easier if you know what you need only a robot to jump around. Now, if you want robots to go through the door, open the fridge, catch the beer, and bring it back to you, you can't do that as easy. And it will be much harder with springs because we don't know how to do it. That's how I see the current situation, how I feel it.
Yeah.
I may be wrong, but
An easier question. Can you tell us more about the book you're working on and when it's going to be published?
oh, so in fact, this is the Handbook of Robotics. It's and Katim. So it's you have the first edition, which already exists, which is a big red book. And so it has chapters on everything in robotics. So I have one chapter on dynamics, one chapter on kinematics, and then it goes into further refined. There's like one chapter on locomotion and one chapter on space robots and things like that. So it's a big book that you can already buy for a lot of bucks. It's not the best book to learn things, maybe. But it's a good reference book because it has everything. And all the chapters are written by knowledgeable people, if I can say that, knowledgeable person on leg robots. But you have the best specialists on, some of the best specialists on each chapter. So it's a fair enough reference. So the first edition went out 3 years ago. The chapter on leg locomotion was written by my PhD advisor, Pierre-Brice, and Kajita. So they wrote this chapter at that time. For the second edition, which should go out next year, most of the authors are changed, but they changed some. Kajita wrote a paper with Christian Ott on limbed robots, and I wrote this paper. I rewrote the chapter on locomotion with first week. But most of the chapters on visual servoing, on dynamics, on redundant robots are written with this. So just any more questions? I think it's time to have lunch.
Yeah, thanks a lot.